Hello, in this presentation we're going to talk about pH and pKa. So let's look for a second at conjugates. Let's use our generic weak acid in water. Weak acids will form our conjugate base and H3O+. Be conscious of what acids they're using in the examples on your AP exam, because more often than not it will not just be a generic A. That's a mistake I've seen fairly frequently, is that people will use the generics when you really should be using or plugging in whatever acid is actually present in the question. Anyway, so if this is your acid, this is your conjugate base, right? When this acid reacts with something, like reacts with a base of some kind, it's also going to form that conjugate base and water. So again, acid, conjugate base. When you have half of the acid reacted, then your acid and conjugate base concentrations will be equal. Let's look at that from the form of a BCA chart. BCA chart uses moles. So let's say, for example, we don't include water, right? We don't have any of the conjugate base at the beginning. Let's say we have, let's say we have 4 moles of our weak acid and we're reacting it with 2 moles of hydroxide. Remember, whichever one's smaller will get completely used up. So this will go down by 2, this will go down by 2, and this will go up by 2. So I'm left with 2 moles of the weak acid. The conjugate, or the strong base, is completely gone, and the conjugate base has 2 moles as well. So notice when you're half of the way to equivalence point, to where the moles equal each other out, your weak acid and your conjugate base wind up equal at equilibrium, and that's really important. At half equivalence point, excuse me, they're equal at half equivalence point. So at this point, we know that pH is going to be equal to the pKa because these things are equal. So that's for half equivalence point. If we're before half equivalence point, so let's think about our titration curve, right? This half equivalence point is what we've been talking about. Before half equivalence point, I have more of the weak acid present. So when I have more of the weak acid present, my pH will be less than my pKa. And you can see that on the titration curve really easily, but you have more acid, so it's got to be less than the pKa. Past equivalence point, or I'm sorry, past half equivalence point, but before equivalence point, then you have your HA is less than your A minus. Your acid is less than your conjugate base. So your pH will be greater than the pKa. And so it's useful to know like these two relationships for before and after the half equivalence point, because it makes it really easy to predict what's going to happen. So let's talk about indicators. Indicators change color when the pH changes, and it works by reacting with either water or hydroxide or the hydronium present in the solution. So our generic equation is HIN, where IN stands for indicator. When the indicator is in water, it will form H3O+ and that IN negative. All right. So just like any weak acid reaction. But what makes indicator special is that HIN will be one color, color A, and IN negative will be a different color. So as we're shifting our equilibrium position to have more of the weak acid versus more of the conjugate base, you're going to see a color change. And it will be right in the middle when the pH is equal to the pKa, because I have the same amount of HIN and IN negative, should be pKa. And so you'll have like right in the middle color of those two things. Now, it's not perfect, right? You're going to have a color change kind of start before this point, and it'll go a little bit after this point. So we usually say it's the pKa plus or minus 1. So if you'll have like 1 pH unit lower, you'll have more of the acid present, but it'll just start kind of faintly changing color. And then 1 pH unit higher, again, it will just kind of fade away the color change. Okay, so it's kind of that plus or minus 1 scenario. But in order for this to happen, it's whatever you have extra of needs to react with your indicator. Okay. So indicators will always kind of throw off your actual acid-base reaction just a little bit because the indicator has to react with something in order to change color. So let's look at our titration curves. Right. So if I have a strong acid-base titration, we know that the pH at equivalence point will be 7. For a weak acid, the pH at equivalence point will be above 7. And you always want to make sure that your indicator that you choose changes color as close to the equivalence point as possible. Ideally, it's going to be right at the equivalence point, but it might be a little bit after. You don't want it to be before, because if it changes color before, you're not sure that you've actually even reached equivalence point. So you want to make sure that it is just after. So most of the time in titrations we'll say you want to just barely see a color change. Okay. And I say just after because you would need just a little bit of excess titrant to react with the indicator in order to change its color. So that's why we use the term end point. So if the equivalence point is right at pH 7 for strong acid, strong base, that's right when the moles of the strong acid are equal to the moles of the strong base, then there would be nothing there to react with the indicator and change its color. So the point where the indicator changes color is when you have just a little bit extra titrant, and that is called the end point. And hopefully that is as small as possible, but depending on what indicator you choose, it might be a little bit more, a little bit less, because each indicator is going to change in a different spot. So you just want to pick just a little bit higher. Like that. It would be the end point, you know. So different titrations are going to have different indicators that are the most appropriate. And of course, if we use a base, start out with a base, you're definitely going to have a different indicator because you want it to change after the equivalence point. And the equivalence point for a weak base strong acid titration is below 7. So you'll definitely want it to be a different indicator than you'd use for the other ones. So you need to be able to choose an appropriate indicator and explain what's going on with the pKa there. So you're looking for the indicator to change color right around that equivalence point. We call that the end point. So you'll pick an indicator based on its pKa. The pKa needs to be close to the equivalence point of your other reaction because the pKa is when the indicator will be changing color. Just a little bit before the pKa and just a little bit after the pKa. So you'll see that color range. So here's a good picture that shows some different indicators and how they change color at these different pHs. And right in the middle is going to be where that pKa is. So like, let me pick a common one. Bromophenol blue here is a pretty common one. It changes from yellow to blue, and right in the middle is the green color. And it's just a little bit less than 4 is its pKa because that's right in the middle of that color changing range. And it's roughly 1 pH unit below, and above is where the total overall changes. Right. Bromophenol blue is a pretty common one. Methyl orange is another common one. It has a little bit broader range based on its structure. Methyl red is a pretty common one. Phenolphthalein is one that you'll see probably the most often. It changes above 7, So it's useful when you're doing, you're starting with an acid and adding in a strong base. And then this last one is a universal indicator. Universal indicator actually is like 4 different indicators in the same solution. So you'll see a change in color across a really, really wide pH range. And again, you want, so that right in the middle will be the pKa, and you want that to match the pH at equivalence point as close as possible to your reaction that you're testing. Okay, so here's an example. We have this indicator, alizarin red. It's an acid-base indicator. Changes from red at pH 4 to yellow pH 5.5. And so its pKa is going to be kind of right in the middle of that. So kind of like 4.75, 4.8 is about the pKa. All right, now it says, would the protonated or the deprotonated form of alizarin red S be red? And explain your reasoning. So I like to write out the generic indicator reaction. Here I'll use the abbreviated form without the water. So this is called the protonated form because it has that proton, that hydrogen ion. This is called the deprotonated form because it's not attached to that hydrogen ion. And then it says, would the protonated or deprotonated form be red? And so red is at a lower pH. So you're going to have more hydrogen ions, which will shift the equilibrium toward the reactants. So you'll have more of them in the protonated form. And you can use the Chatelier's principle to explain it, but you can just say more would be in the protonated form at a lower pH, and it's a red at a pH of 4, which is lower. Would this indicator be the most effective for a titration with sodium hydroxide of acetic acid or the titration of hydrochloric acid? So if we had to pick, right, weak acids will look like this, and at equivalence point that's above 7. I'm not to scale. Whereas with a strong acid, with a strong base, the pH at equivalence point is exactly 7. So, you know, neither of these would alizarin red S would be the best choice. But if I had to pick between the two, it's slightly better for the hydrochloric acid because the pH at equivalence point is lower versus a weak acid. It's going to be above 7. Yes. Okay, so now we have nitrous acid, and they give us the pKa is 3.16. We make a buffer solution by mixing it with sodium nitrite, and then we add in bromophenol blue. A blue color can be observed. Which species is present in a greater amount, the protonated HNO2 or the deprotonated NO2 minus? If you were to look at the chart from a few slides ago, bromophenol blue changes in a range of about pH 3 to about pH 4.6, and it has a pKa value of about 4. Okay, and then it changes color from yellow at pH of 3 to like a dark blue or purple at pH 4.6. So when bromophenol blue is added to the blue color can be observed, so it's on the higher range. And remember, color is kind of subjective. Yeah. So it says the pKa of nitrous acid is 3.16. All right, let's write our weak acid dissociation just so we can visualize it. So this is protonated, and this is the deprotonated. Blue color can be observed, so we know that it's going to be a higher pH than the pKa. So pH must be higher than the pKa of this weak acid because we know it's on like the 4.6 range, so it's higher than the 3.16. And because the pH is greater than the pKa, I know that for my weak acid, I will have more of the conjugate base present. So that means I'm going to have more of this side of the reaction, so more of the deprotonated form will be present.